All right, so this time, this is a little different problem because it's not just dealing with shape, okay? We're dealing with a scenario, and we've got an observer. They're standing 500 feet away from a launch pad. So I'm just going to go ahead and start drawing a picture here. A problem like this is I just need to draw a picture. So I'm just going to make 2 points. Here's the observer, and here's the launch pad. And the distance between these two is 500 feet. I mean, you want to, basically you want your pictures to end up being a basic shape. That's what you want in the end. So don't try to make it fancy or anything. So observer, launch pad, 500 feet. The rocket blasts off and maintains a velocity. So the rocket goes up from the launch pad, and it maintains a velocity of 700 feet per second going up. Assume that the scenario can be modeled as a right triangle. So what I'm going to do now is I'm going to, isn't this a right angle that I just drew? If the rocket goes straight up and I'm standing on the ground, this is going to be my right triangle. How fast is the observer to rocket distance changing? So where in my triangle would be the observer to rocket distance changing? That's the hypotenuse. So I'm looking for the rate of change of that side. Okay, so what side do you want to call that? Okay, notice I labeled my triangle OLR. What is that side called then? That's called L, side L. If this is angle L, this is side L. No, we don't want to use two things. We want to use one thing to name the sides of a right triangle. So L, so if this is side L, what's the rate of change of L? dl over dt. Could you just use x, y, z? Could you use ABC for your sides? Yeah. See, the whole thing is this isn't like a volume or an area problem. It ends up being just a Pythagorean theorem problem because we have a right triangle. So we just can name the sides whatever we want. So dl over dt, that is what we're looking for. How fast is this hypotenuse changing? So that's what we want to find. So what would this side be called over here? What is the letter name for 500? R. And what is the letter name for 700 feet per second? It's not O. How do you know it's not O? It's a rate of change. How do you know it's a rate of change? Per second. So what has to go with it? Is it this side O? And so what would this be? D over dt? It's kind of weird. I don't know. That's okay. Again, I could have used any three letters that I wanted to. Okay, so do I know anything else? How fast is 1200 goes where? That's O, good. So O is 1200. Okay, so there's only one thing we don't know. What's that? Well, no, I don't know L either. Don't I need to know L? I probably do. How do you find L? Pythagorean theorem. 500 squared plus 1200 squared, and then square root it. You can give a decimal. I got 1300. So L is 1300 feet. Okay, so the advantage, step one, we know all of the things. We're only missing one thing, and now we've got to come up with an equation. So that's step one we did right here. I guess step two, I probably don't want to do it up here, so I'll do step two here. So what equation relates these three sides? What did we already use once? Pythagorean theorem, a squared, b squared, c squared. So instead of a squared, b squared, c squared, we have o squared plus r squared equals l squared. So derivative, step three. Take the derivative of o squared. 2o times do over dt. Plus, what's the derivative of r squared? 2. Yep. Okay, plus, or equals, sorry, not plus, equals the derivative of L squared, 2L times dl over dt. Okay. So now what do we do in step 4? Plug things in. So what was O? O is 700, so 2 times 700. What is dO over dt? O is 1200. So can I just say 2 times 700 times 1200? Because isn't dO over t 700? So dO over dt is 700 and O is 1200, okay. Plus 2 times, what's R? 500. Now, what is the rate of change of, how fast is this distance changing? It's not. This dr over dt is 0. Don't you stand in one spot and is the launch pad going to move? No, it's really heavy. It takes a long time to move it, like weeks. Okay? So this dr over dt is 0. Equals 2 times, what's L? 1300 times dl over dt. Okay, so now, isn't that gone? So 2 times 700 times 1200 is 1,680,000 equals 26,000 dl over dt. And then just divide by 26, not 26,000, 2,600, sorry. So the rate of change of the distance between the observer and the rocket, the rate of change of that is 646.15. What? What would be the label? What was the label on the dO over dt? Feet per second. All right, so I'm just going to take a look at I'm going to skip number 5 and we're going to look at number 6 right now. So we've got a conical paper cup that is 30 centimeters tall with a radius of 10 centimeters. And the cup is being filled with water at a rate of 2 pi over 3 centimeters cubed per minute. How fast is the water level rising when the water level is 2 centimeters? So a conical paper cup, wouldn't it have to look like this? I'm going to draw the picture up here. It's okay. Isn't that the conical paper cup? Cone? Okay, so the cone would have what labels? What dimension would that be? Okay, but what letter goes with it? R, that's the radius, that's 10. Okay, that's at the top. And the height, what's that? Okay, so the height is 30 centimeters. Okay, so what's dH over dt? Basically, here's what you need to realize. For every dimension, it has a rate of change, or it doesn't. But, the rate of change could be 0. So, do I know the rate of change of the height? Also, do I know the rate of change of the radius? And then I'm dealing with the volume, so the volume and the rate of change of the volume. So something else you can use too is that if you know what shape you're dealing with, you can just write down, well, what are all the dimensions that I would have of that? I should be able to find all but one of those. All but one of those. So, I've used the 30 and the 10. And what's 2 pi over 3 centimeters cubed per minute? Rate of change of what? How do you know it's the volume? Because it's cubed. So this is dV over dt. And where is the 2 centimeters? Now see, this is where it gets kind of confusing because I'm telling you the height of the whole thing is 30 centimeters. But what is this scenario telling us that's happening? Is it filled all the way to the 30 centimeters? It's only filled to the 2 centimeters. So I might not want to be so fast at calling the height 30 centimeters. I can label the picture as this being 30 centimeters and the radius as being 10 centimeters. But here's what I'm interested in. I'm interested in when it's only filled up to here. I'm interested when this is 2 centimeters. Now, tell me about the radius when it's only filled to 2 centimeters. Is the radius when it's only filled to 2 centimeters? Is it 10 centimeters? No. Okay, so we've got some things that we can't really figure out right now. Don't we? Okay. So, well, I'm just going to move on. We're just going to write the volume formula and see if we can, and we'll figure stuff out as we go. Okay, so let's write our volume formula and see if that gives us any hint on what to do. So what's the volume of a cone? Well, I'll tell you, it's 1/3 pi r squared h. That's the volume of a cone. Okay, so now, here's the deal. We typically, if I were to take this derivative right now, what rule would I have to use for both of these? Product, because I'd have to take this would be like your first and this would be like your second. And so then I'd have like a dh over dt and dr over dt. Now look back at the information we wrote down. Did we know either one of those, dh over dt or dr over dt? No, we didn't. So if we do this derivative right now, we'll have dh over dt and dr over dt, which we don't know. So there'll be too many things we don't know. So whenever you're dealing with a cone, a triangle type problem, there's a little relationship that you have to do, and you learned about similar triangles in geometry. Do you remember similar triangles in geometry? So what I can do to relate the r and the h, basically I want to change to just h. I want to change it to just h instead of r and h. Change it to just h instead of r and h, and then take the derivative. So here's what I know. You see this big triangle right here? The 10 and 30? Isn't this little triangle in here similar? So we're looking at a ratio of radius over height. Would you agree? Radius over height? Or height over radius. It really doesn't matter. So for this similar triangle, I'm just going to draw it right down here. We've got radius and height. That's the main thing. So radius over height. Okay, well, what's our main radius and height? Well, that's 10 over 30, correct? What is our similar triangle's height that we are dealing with? 2, and we don't know the radius, correct? Okay. No, I don't want the, never mind, get rid of the 2, r over h. So, back up. All we want to do is say r over h equals 10 over 30. The 2 is actually going to be RH in the problem that we plug in, because that's the height we're interested in. So we take our general dimensions, radius over height equals 10 over 30. Would you agree, is that a ratio? Yes. Okay, would you agree that my little, however high I fill it up at any given point, that it will have that same ratio of 1 to 3? Okay. So what would r equal if I rearrange this equation? Get r by itself. How do you get r by itself? Multiply by h. So isn't r equal to 1/3 h, or h over 3? So what could I go and replace the r with? So I'm going to take my volume formula. This is step 2. This is my equation now. My volume formula is 1/3 pi times, well, I'm going to replace the r squared, r with h over 3. I'm going to have to square it, and then times h. Now, why are we doing all this? Because I have too many variables in my original problem. Too many variables. If I take the derivative of this right now, I'll have dr over dt and dh over dt, which I didn't know. So we're using the fact that similar triangles allow us to write the radius in terms of height and substitute it in. Now let's simplify this volume formula. What's h squared, h over 3 quantity squared? Isn't it h squared over 9 times h? And what's h squared times h? H cubed. Okay. And 1/3 times 1/9. Isn't there a 3 and a 9 on the bottom?